Hello everyone. We are now going to begin our study of a special kind of probability called the binomial probability. Now, the word bi suggests two. So, binomial probabilities have to do with experiments that have only two outcomes. For example, tossing a coin, right? When the experiment of tossing a coin will result in two possible outcomes, either getting a head or a tail. So that is is an experiment that has to do with binomial probability. Another example would be when we want to know whether something happened or did not happen. Did the students pass or did they not pass? Is a person alive or is not alive? So these are situations where the outcome is going to be just two. All right. So those probabilities are called binomial probability, and we give a special name to the experiments which we will learn as we go on. They would be referred to as Bernoulli trials, but we will get to that later on. But let's get started with this chapter at this point. These are some of the topics that we are going to cover in this lecture. First of all is something called factorial. So factorials is an operation which is performed on discrete numbers, and in order to calculate binomial probabilities we will have to know about factorials and how to calculate factorials. And then once we know how to calculate the factorials, we will go into the formula for binomial probability. And then we will learn about the mean of binomial distributions and to calculate the standard deviations of binomial distributions. A factorial is an operation performed on discrete numerical values. Just like we have the addition, subtraction, multiplication, and division, those are operations performed on numerical values, any numerical values, whether they be decimal values or uh, integer values. Factorials are operations worked on discrete values, discrete numerical values. So the values that we will work with will be positive integers, right? So let's see what it says here. The factorials, the definition, the product of the first k positive integers or counting numbers, that's what discrete values mean, is called k factorial and is denoted k and then an exclamation point, k followed by an exclamation point. And the way we calculate it is k factorial. So instead of saying exclamation point, I'm going to say k factorial is equal to k times the k minus 1 times k minus 2 times k minus 3 all the way to 1. All right, so I'm going to work on some examples, but 0 factorial is a value, is a constant value, is 1. But let me describe what with an example, with a number, how to calculate a factorial of a number. So 5 factorial, I'm going to just take this value here, 5 factorial, all right? So when you see an exclamation point next to uh, an integer value, that means it suggests factorial. So you have to start to calculate, to perform the calculation. You have to start from the value 5, so 5, and multiply it by the next lower number. So 5 minus 1, 5 minus 1, which is a 4. Then take the 4 and 5 times 4 times 3, which is 1 less than 4, multiplied by 1 less than 3, which is a 2, multiplied by 1 less than 2, which is a 1, and you stop here. So 5 factorial would be a value which is 5 times 4, 20, 20 times 3, 60 times 2, 120, and that's what 5 factorial is. So that is how you calculate factorials. You start with the number whose factorial you want to find. In this case, it was 5, and then multiply it by the by a value 1 less than 5, which is a 4, multiplied by 1 less than 4, which is a 3, multiplied by 1 less than 3, which is a 2, and you stop at 1, and then you multiply it all out, and whatever the value is your answer, is the calculated value for the factorial of that number. All right, so we will go into some examples, but keep in mind always that 0 factorial is not 0. 0 factorial equals 1 always. So if you're given a non-zero positive number, then this is how you do the calculation. But if somebody asks you what is 0 factorial, the answer is always 1. We will now discuss an application of factorials. One area of application is called binomial coefficients. Now it's called binomial coefficients because it's commonly used to find the coefficients in a binomial expansion. What is a binomial expansion? We have studied in algebra the expressions as a plus b whole squared, which when expanded gives us a squared plus 2ab plus b squared. And then we also had learned a plus b whole cube, and there were formulas associated with these expansions of squares and cube. And when we expanded a plus b whole cube, we got a cube plus 3a squared b plus 3ab squared plus b cube, and so on, correct? Now, in order to expand binomials of higher degrees, so something like perhaps a plus b to the power 7 or a plus b whole 12, right? In these cases, for every exponential expansion, it's not possible to memorize all these formulas, but using the binomial coefficient, to which there is also a formula that we will learn about, using binomial coefficients, we can expand any binomial following or using this formula and following a pattern in which these variables and their exponents appear in each term. All right, so because this formula is very useful to expand binomial, it gives the coefficients of every term. That's the reason it's called binomial coefficients. Now, the same formula can be used in another area, and that's when we want to know the number of unique combinations that can be created, number of unique combinations of a certain size, I must add, from a list of values, from a certain number of values, right? So let me write that down, that application. All right, it tells us how many ways we can create unique combinations of a certain size, which we will denote with the letter X, from a given number which we will call n of values. Given number of a list of values, let's say we need each value also, list of values, right? So it says how many ways we can create unique combinations of a certain size denoted by the symbol x from a given number or n of a list of values, and that formula is n factorial divided by x factorial times multiplication times n minus x factorial. And note this factorial, this exclamation point is outside the bracket. So first you have to evaluate n minus x and then find the factorial and then multiply that value by x factorial and then perform this division to get, it'll tell us how many ways we can create unique combinations of size x from n number of values. Okay, so we will work on examples of this in our worksheet, all right, because the whole entire problem to create or to evaluate binomial probabilities. Binomial probabilities, when we get there, will use this formula for binomial coefficients in its own formula. All right, so it's a little bit long drawn process, so we will go through that in a worksheet example. Here we will discuss some of the properties of experiments that give us binomial outcomes. Now they are called Bernoulli trials, named after the mathematician and scientist who researched on binomial probabilities. These trials, Bernoulli trials, are repeated trials of an experiment, and they will satisfy certain conditions. So let's read through it first. Repeated trials of an experiment are called Bernoulli trials if the following three conditions are satisfied. Number one, the experiment, each trial, has two possible outcomes denoted generically S for success and F for failure. So it depends on what you are looking for. When you toss a coin, if you hope it'll land on an H, on a head, and it does land on a head when you toss it, then it's considered a success. The outcome is considered a success. If on the other hand, if it lands on a tail, it will be regarded as a failure. All right. So whether it's going to be success or a failure is dependent on what outcome you are looking for, the outcome you are studying. Number two says the trials are independent, meaning that the outcome on one trial in no way affects the outcome on other trials. Remember, we talked about dependent and independent events, right? Now, Bernoulli trials must always be independent event. One example we discussed in a previous lecture was the gender of a child at each birth, gender of a baby at each birth. They were independent events. Whether you have a boy or a girl in the first birth is the same as what you would have, what you could expect. The probability of having a boy or a girl in the second birth is the same as the probability of having a boy or a girl in the third birth and in every subsequent births. All right. What you had in what you're going to have, or what somebody is going to have, whether the gender is going to be a boy or a girl in the second or the third birth, is not dependent on what happened in the previous birth. That's what independent trials, independent events, and therefore independent probabilities are about. So number 3 says the probability of a success, called the success probability and denoted by the letter P, remains the same from trial to trial. All right. So those 3 are the properties of Bernoulli trial, and Bernoulli trials will always have 2 outcomes. We are going to go here over an example of binomial distribution. Now, binomial distribution is nothing but the probability distribution of every outcome from a Bernoulli trial or an experiment, all right, or a binomial experiment, so to speak. Now, this study is based on the outcomes and probabilities for observing whether each of 3 people is alive at age 65. Sometimes insurance companies who give out life insurance policies to decide on a premium when a policy is started, they want to know typically up to what age a person survives. All right. So this is an application in the field of actuarials, and uh, you know, insurance companies typically often do these kind of studies, but it's often used for in other areas as well. All right. Now, this particular example we will work through completely using the binomial probability formula and so on in one of our worksheets. So you may want to go through that in detail, but here we are going to introduce the example and look at the probability distribution, how we come up with the probabilities for each outcome using the properties of Bernoulli trials also. All right. So we begin by creating a tree and determining all the possible outcomes. Now, the success probability, all right, the success probability, that means observing, or the probability of finding a person alive at age 65, is, the probability is 0.8. Okay, the probability, this is the success probability. And it's not written here, well, it is written, but it's not written explicitly, but I know it because this is a problem from the book, and that's the probability, success probability value that's being used. All right. So P equals 0.8, which is the success probability. Now, if P is 0.8, then the failure probability is going to be 1 minus 0.8, which is going to be equal to 0.2. All right. So the success probability is 0.8. Now, in our case, we are looking for whether a person is alive at age 65. That's going to be our success. If we find the person is no longer living at age 65, that means that's a case of failure, because that's not what we are interested in. We are looking for somebody to be alive. So failure probability is calculated 1 minus 0.8, or whatever the success probability is, and that's the value we are going to use if we find somebody is not alive at age 65. And then we go on to building a tree. We are looking for 3 people drawn at random, right? So we have to have 3 draws in our trial. Now, in the first draw, we can end up with a person who's alive or not alive, correct? S and F. So what is the probability of finding a person in the first draw who's alive? That's the success probability, which is 0.8. What is the probability of finding a person not alive? That's 0.2. That's the failure probability. All right, so 0.2. So that was the probability of success and failure in the first draw. Then we draw another person, another um, um, we perform another trial, so to speak. Now, if we had success in the first draw, that means the person was alive in the first draw, then in the second draw, we can, with the same probability, we can find another person alive or another person dead. So the the probability of finding a person alive, given that the person we already got a person who was alive in the first draw, is going to be the same. Again, that's by the property of Bernoulli trials. So it's again going to be 0.8. The probability of finding a person not alive in the second draw is still going to be 0.2. For the third draw, for a person to be alive, success, it's 0.8. The probability of failure is 0.2. All right, and in this way we construct our tree with 3 draws, and then we walk this tree to list all the outcomes. So SSS, that's our first outcome. SSF, we list that. Then SFS, SFS, SFF, and so on. And then we walk the tree. On the other side, if we had started with failure, then the probability of getting a success or a failure in the second draw would still be the same, right? And then in the third draw also the probabilities would be the same, correct? These are independent trials, and the probabilities are also independent of whatever happened in the previous draw. So here we list all our outcomes, and now we have to calculate the probabilities. So what do? We use what's called the multiplication rule for independent events, and that's just multiply the probabilities at each draw. So SSS would be 0.8 times 0.8 times 0.8 for a probability value of 0.512. 0.8 plus 0.8 plus times, sorry, not plus. If I said a plus before, please pardon me. It should be multiplication. 0.8 times 0.8 times 0.8. 0.8 times 0.8 times 0.2 is 0.128. And likewise, we go through each of these outcomes and calculate the probability values. All right. So that's what we are showing or doing to come up with the probability distribution. Now let's say we want to know what is the probability of uh, finding 2 successes. What is the probability of getting 2 successes in our experiment or from our experiment? All right. So probability, let me write that down. We are looking for the probability of 2 success. How would we calculate that? We have to go through our outcomes and find how many ways we can have 2 successes. So we see here this has 2 successes. exactly two successes. Let's be precise about that. Exactly two successes. SSF has two success. SFS has two success. Then FSS has two success. And just these three, correct? These three. The other ones have one success, and this one has three successes. So the probability of exactly two successes is, well, how do we do that? We would now use a special addition rule where we just sum up, right? It would be probability of SSF, right? It would be probability of SSF or SFS or SFSS, correct? So what would we do? We would go about adding 0.128 plus 0.128 plus 0.128, which would be 3 times 0.128, isn't it? All right, and that would be the total probability of getting exactly two successes. What we are going to do next is come up with a probability formula, a binomial probability formula, which will help us to find the probability values without having to draw all these, draw all the trees, come up with all the outcomes, calculate each individual probability, and then figuring out how many ways we can get two successes or one successes or two failures, and then look up this table to do all this calculation. This is time consuming, especially if we are working with a complex real life application problem. The binomial probability that we are going to see next will tell us exactly, will give us a way of doing this calculation much faster for a specific case. All right. If we are looking for probability of exactly two success, we can just plug in values into the formula and come up with the value. Or if we want to know how many, what it would be the probability of getting no successes, again, just use the formula instead of going through all this work, right? Now, while talking about binomial distribution, this tells us the number of outcomes containing a specified number of successes can be determined by using the binomial coefficient formula. All right, so if n Bernoulli trials, or in n Bernoulli trials, the number of outcomes that contain exactly x successes equals the binomial coefficient, right? Previously, we said, uh, remember what we just discussed in the previous slide was how many ways we were trying to determine how many ways we can get two successes. We can get exactly two successes. All right, and we found there were three ways in which we could get two successes. It could be SSF or SFS, or it could be FSS. And what did we do to calculate the probability? We just took each of these had probability, I think 0.128, 0.128, and 0.128. So what we did essentially was there were 3 times 0.128, so we did 3 times 0.128, and whatever that calculated to was our probability answer. What the Bernoulli, the binomial coefficient will help us find is this value here. How many ways a certain success situation can occur. All right. So without having to look up a distribution table, we can use the binomial coefficient formula and know in how many ways, that means uh, the unique combinations that will give us a specified number of success. In this case, it was 3, but depending on what the experiment is, it would be a different value. All right. And then to calculate the probabilities, we will, to calculate this part, 0.128, we will need to go further into the binomial probability formula. Okay, we are at last at the binomial probability formula. Let's first read through it. It says, let X denote the total number of successes in n Bernoulli trials with success probability P. Then the probability distribution of the random variable X is given by probability of X equals, the formula is right here, n combination X, which is the binomial coefficient formula. So how many ways we can get a success situation from the total number of trials, in this case, n and x. It's written like this. That's the way we denote binomial coefficients. And then p, which would represent the success probability raised to the power x, times the failure probability, which is 1 minus p raised to the power n minus x, where x can take values between 0 and up to n. All right. The random variable x is called a binomial random variable and is said to have the binomial distribution with parameters n and p. The steps to find binomial probability are all listed at this point. So to find a binomial probability formula, we first have to make sure that these assumptions are met. It has to be a Bernoulli trial. Number 1, n trials are to be performed. Number 2, 2 outcomes, success or failure, are possible for each trial. So it should be a case of binomial probability. Then each of the trials are independent of whatever happened previously. Number 4, the success probability P remains the same from trial to trial. All right, so essentially we have to make sure that it's a case of Bernoulli trial. It satisfies the properties of a Bernoulli trial. And once all these are met, then we go into performing the steps. Step 1 is to identify a success, all right, because we first need to identify a success, otherwise we will not be able to assign the success probability values or the failure probability values accordingly and correctly. Step 2, determine P. We have to know what the success probability is. So P is always associated with the success. So determine P, the success probability. Step 3, determine N, the number of trials. And then the binomial probability formula is going to be used for the number of successes we are looking for is N. This is the formula, we just saw this previously. So the probability that X, that means the success is going to be a particular value, say 0 or 1 or 2 or 3 or n, is given by this formula, n combination x, p raised to the power x times 1 minus p raised to the power n minus x. Here we talk about finding the mean and standard deviation of a binomial random variable. Now, it's a very simple formula. This is probably the easiest formula we will get to calculate the mean and the standard deviation. So mean is calculated using the formula n times p. So we have to know n, how many trials we are going through in our experiment, and p is the success probability. Multiply the two and that is your mean. Standard deviation is square root over n times p, which is the mean, correct? We just calculated mean, n times p multiplied by the failure probability 1 minus p. And then, of course, you have to take the square root of it. So that's the formula for the mean and the standard deviation of a binomial random variable. Whether a distribution, a binomial probability distribution, is going to be right skewed or symmetric or left skewed depends on the value of the success probability. If the success probability is less than zero point 0.5, or let's start with the symmetric situation. If the probability value, success probability value is 0 0.5 or very close to it, then it's going to be a symmetric distribution, a normal symmetric distribution. If, on the other hand, the probability value is less than 0.5, right? If it's less than 0.5, then it's going to be a right skewed distribution. If the probability value is 0.75, then it's going to be a left skewed distribution, right? So we have to remember these rules, because if we get a question asking what is the distribution, then we have to remember the rules, whether it's symmetric, right skewed, or left skewed. So that example that we were just talking about, 3 people being alive at age 65, if you recall, had a success probability equals 0.8, correct? That was the value of p we were using to calculate the probabilities for different outcomes. Based on this, all right, if we are asked what would be the distribution, if it would be symmetric, right, or left skewed, we would have to look at the probability value and see if it is less than 0.5 or greater than 0.5. In this case, it's definitely not equal to 0.5. We can see that, so it's not going to be symmetric. We have to see whether it's less than or greater than. It's greater than 0.5, it's 0.8, so that means it's going to be a left skewed distribution. A left skewed distribution. So that is how we determine the nature of the distribution from a binomial, or of a binomial uh, distribution, rather, uh, for a binomial uh, probability distribution. Now, this last slide on this topic gives us a relationship between sampling and binomial distribution. Suppose that a simple random sample of size n is taken from a finite population in which the proportion of members that have a specified attribute is p. Then the number of members sampled that have the specified attribute has exactly a binomial distribution with parameters n and p if the sampling is done with replacement, and has approximately a binomial distribution with parameters n and p if the sampling is done without replacement and the sample size does not exceed 5% of the population size. So the two situations, or the difference between these two points here, is that if it is done with replacement, then the number of members sampled, that will meet the success attribute will have an exactly binomial distribution, and these of course are the related parameters. So the keywords here are number of members sampled meeting the specified attribute. The keywords would be exact binomial distribution, and it has to be with replacement. In the second case, it's without replacement. So if the sampling is done without replacement, then the distribution would be an approximate binomial distribution. All right. So, but the conditions that also that the sample size should not exceed 5% of the population size. Right. So this is just coming up with a relationship between sampling and binomial distribution, and how many members, the number of members in the sample that would meet specified attribute.